Hi, Guy Moxey from Wolfspeed Power, and welcome to another episode of In the Studio. And today's going to be an interesting one because we are joined by Mr. Cengiz Balkas, who is head of our materials business here at Wolfspeed. Cengiz, welcome.
Hello, Guy. Good to be here.
Pleasure to have you. So Cengiz, thanks for joining us today because this is a very exciting subject, materials, for wide bandgap in general.
Yeah.
And it's the kind of the dark arts. It's what people in the industry hear a lot about but never see. But they hear about how difficult it is and how Wolfspeed and in its previous incarnation as Cree was leading and pioneering this area for the past 32 years. And it's been your gig.
Yeah. You know, certainly there is a dark art nature to it, but at the end of the day, it is a engineering topic. However, the way you go about making silicon carbide crystals and turn them into wafers, you know, it starts at very high temperatures, so entropy is your enemy, and bringing order to that takes time. I think that's what we've shown at Cree, especially at Cree times and also now at Wolfspeed. It takes a lot of learning, cycles of learning to get to a commercially viable platform. On top of that, you know, work on expanding the materials diameter for new generations. So when you add all that out, it is a difficult subject for sure. And you know, I think every year we reduce the dark art some, but it's still there.
It has that mystique to it. You know, you're certainly not Lord Voldemort, absolutely not. But taking a step back, you know, how did you get into this side of the technology? Because it's not the most visible. And I don't know, but when you were in your early teens, did you want to be a materials scientist? You know, how did this all unfold?
Well, I think it was a little bit of luck to be in the materials science department for my undergrad studies because, you know, you can make a choice of different engineering topics and this one appealed to me. Not a particular importance there when I made that selection. But then when I came to the States, to NC, North Carolina State University, that research group had just given birth to Cree 4 years ago.
John Palmer and
Calvin Carter and so on. So, you know, I fell into a wide bandgap group at the university. So I worked in nitrides, but we were always very close to silicon carbide. And after I got my PhD, went to a silicon carbide crystal growth and wafer company, and here we are. That was back in 1998. So
1998 was way before wide bandgap was even a twinkle in people's minds, to be honest. You know, commercially accepted. So this is well ahead of the curve stuff.
You know, it is. In those days, of course, you know, nitrides combined with silicon carbide as a substrate, it was pretty widely used in LED work, blue LEDs. So, but for power electronics and RF electronics, you know, wide bandgaps were still developing in those days. But, you know, I don't know, we kind of grew up with this notion of how good the material is and what it could turn into at the device level. So we always found enough audience, I think, to keep, you know, stay excited about it. And certainly Cree had a massive advantage being in this business because, you know, our LED business was built on silicon carbide wafers.
That's right.
Yeah. So that inevitably required scale in crystal growth. So, you know, a lot of the good work in the early days was done because of that. LED, very competitive business. You can't have expensive wafers, so that put a lot of pressure on the material side of the business to create, you know, commercially viable substrates. But in time, you know, power and RF applications continue to evolve, and you know, initially the GaN HEMTs became commercially accepted and viable, and then really, you know, silicon carbide Schottky diodes were in the market, but in 2011 we introduced the silicon carbide MOSFET, and really the market started taking off.
And did you ever dream it would take off to the stage it is now for power and for, of course, Wolfspeed is RF as well?
You know, I did, but I didn't realize how it will feel when it gets big. we always were excited from grad school, writing papers. It's going to be big. It's going to be big. We always said this, right? So it's really different experiencing the scale it has. Yeah, and honestly, we're still at the early stages. So when you look ahead, this is going to add a couple more zeros into anything you're measuring. So
it certainly is.
Yeah.
And you made tremendous. You say at the early stages, and I'm an outsider looking in. I'm a power electronics apps guy. So as long as a wafer and as long as the device does what it says on the data sheet, that's all I care about.
Yeah.
But you're 4 levels at the earlier on, 4 or 5 levels in some cases. Tremendous advancements in the last 10 years, more noticeably. I mean, you employed me nearly 10 years ago. Thank you for that, by the way.
It was a great hire.
Thanks. And back in those days, we were 4-inch substrates, 4-inch wafers.
Yeah.
And look where we are today.
Yeah, it is interesting. And when you joined us, and you know this really well because we spend a lot of time on looking for the right application for silicon carbide, right? Because if you look, you could pick from a whole host of applications that some are not ready for commercialization, some are prime for commercialization.
Some have become ready.
Yeah, and in some cases we had to go, create the application reference framework for people to, use silicon carbide. And that was a different time, right? Today, when you look at it, everybody knows what to use silicon carbide for. The main challenge right now is, given the size of the applications that we got into, is how do you create that scale and continue to support the industry. And that has a couple aspects to it. Obviously, the volume is one, but the diameter of the wafer to be used is another one. And as I think you have an appreciation for, increasing wafer diameter in silicon carbide is not an easy task. It just takes time. So, you're right, in the last 10 years a lot has changed, but in the last few years we really started accelerating our work in creating the right quality material in 200 millimeters and also on 150, and then matching that with the capacity behind it, because most of the materials business customers are in automotive related applications or in industrial or energy. There's a lot of volume needs. Specs are very tight. So I think scaling to support that drive in the industry, keeping your volume connected with the needs, and then also the quality of the wafers connected with the requirements of the application. These are new challenges.
Yes. That word scale
Yeah.
is a very important word, because from the material side, from a theoretical into R&D, into prototyping, into mass volume commercialization is some big steps. And we all see, most people in the industry are more familiar with the fact, they start seeing things happen at the fabrication stage, but you're pre-fabrication.
Yeah.
So what is Wolfspeed now doing for that scalability of materials? And materials and EPI as well, because it's combined together.
No, absolutely, you definitely need the EPI. So we have a unique advantage that we always had. Being vertically integrated as a materials supplier to the outside, but also having a device, multiple device groups inside, right? We had feedback coming from our LED group continuously, from our RF group, from our power group. So what this does is it helps, to settle the specs for the material ahead of, commercialization to the outside market. So, we spend today a lot of our energy is inside this vertical integration, concept, because, let's say you change something in the crystal growth of silicon carbide that causes a change in the wafer and the EPI, and then goes into the fab. And there are also things you can introduce at the fab. So how do you discern between what came from materials versus what needs to improve in the fab? This type of challenges for us, we can tackle it a lot faster compared to if somebody is just buying the wafer, getting epitaxy done someplace, and then fabbing it for a device. So I would say today, a lot of the energy is in getting this internal, particularly on the 200 millimeters wafers, getting this feedback back into crystal growth, back into epitaxial process that we run, and then create something better, and then give it back to the fab. So this is the a pretty high level of our energy is going into this. Yeah. Now, in time, in 10, 20 years, this probably will change, but today it's almost a prerequisite if you want to go fast.
Yeah. Within the realms of what you're allowed to say, because I know nothing about material science and the material science business here. I'm not even allowed into the premises. My door pass doesn't let me in.
Good.
Yeah, I would do some serious damage. But within the realms of what you're allowed to say, why is this stuff so difficult? Because everyone reads it's so difficult, and we have people come to us to buy it because it's difficult. So why? Compared to silicon?
Yeah, so if you look at other crystal growth technologies that are, commercially available, first of all, this one is a sublimation recondensation technique, so that's kind of unique. But the temperatures at which this happens, it's pretty crazy. It's around 2,500 degrees
C,
right?
2,000 C.
Yeah, we've said this is half of sun's surface temperature. And they both melt, right? Gallium arsenide and silicon carbide doesn't. It sublimes and it needs to be recondensed. So when you put all this together, and at 2,500 degrees C, you look at, okay, what do you have in terms of materials to work with to grow the crystals in? Your choices are very, very limited, right? It's heavy on graphite content. But the other thing is at 2,500 degrees C, you basically have white light coming out of your crucible. So you don't have your typical semiconductor controls you would have even in an epi system, for example. So that's where, a little bit of the art comes into it, I think, because you have to do a lot of trials to understand how it is. And you need
32 years of trials.
Pretty much. And the oddest thing will come across as something that you didn't pay attention to control, and then you learn, and then you control it. So there's a lot of little, nuances to the crystal growth. And remember, this is all happening at a super high temperature. Yeah. So once you find something to repeat it, it's also not easy. Yeah. Because you're trying to repeat something at a pretty chaotic situation. So
you were writing your own instruction manual?
Pretty much, yeah. I mean, we do have, obviously, the basics are generally known, but the basics don't get you to a commercially viable crystal growth or a wafering system or a, construct. So there's a lot of know-how that we built over the last 35 years, I think. So that all builds in. But with that said, the teams have been fantastic deploying the latest methods in, understanding data, using AI, working with the vendors to get to the next, level of specifications that could help certain attributes in the crystal and the wafers. So it's really an interesting mixture. There's not a simple recipe. You can't go get a tool and be in business, especially at the scale that we're in. Yeah. Right. So we have over $1.3 billion in long-term contracts in the materials business, supplying to the world's top power semi companies. So margin of error is not very large.
That's true. Yes,
so
not particularly forgiving. And you've presented slides at Investor Days saying you've shipped X amount of swimming pool. Football pitch areas of Silicon Carbide.
Yeah, 15 football fields or something. Yeah. And we had, at that time, we had just grown our millionth wafers. But what was really more impressive to me was when the next million comes. It's a lot faster than the first one.
Oh, yeah.
Yeah.
It's exponential.
So the amount of capacity that we deployed in the last, 4 or 5 years is significant. And I think that is really the true test of a good material supplier, how well you can scale it without sacrificing any of your specs, or actually you have to improve your specs because most of our contracts require us to have better specs going forward.
Scalability and consistency.
And lower cost. Yeah. So when you put all of it together, you really need a robust production system that could scale.
So on the scaling question, carrying it further, 200 millimeter.
Yeah.
Think back to silicon. I actually remember 200 millimeter coming in late 80s, early 90s. So, geometry, moving up geometry is not a new thing, but silicon carbide, this is a big deal, isn't it?
It is. Technically, to get to it is not easy, of course. So maybe a couple comments on the 150 first. The 150 millimeter platform we have, it's the backbone of all the long-term agreements we have with our device folks. Also internally, we use a good number of 150 wafers. So in terms of applications driving silicon carbide, 150 absolutely hits the quality and the cost and the volume that you would need to support those applications. Now, we had a chance, and so normally the industry would have gone to 200 anyways, but when we started our new fab in Mohawk Valley, it was clear that that fab is going to serve automotive applications. And the idea of starting it with 150, getting qualified, and then switching it to 200 later on, obviously causes some gaps in the planning.
It's a lot to stomach for an end customer. Yes.
Absolutely, yes. And they're serious automotive customers. So we looked at the 200 millimeter technology. I mean, it was in development, and we said, look, can we accelerate it and meet the timeline? And there was a little bit of risk in the decision, but our CEO made all of us comment and say yes or no on it. So we did it. It was all let's go for it. So. Today we've already demonstrated some very high quality 200 millimeter wafers. We're working on the cost side and the volume side. Those two need to, come. They need to get better. But so that transition, we're going to do it internally a little bit ahead of the commercial markets.
Okay.
But again, if you talk to our customers and ask their view on 150 millimeters and the longevity of it, given the customers they serve, it's actually it's gonna be around for a long time.
Oh, yeah.
And we intend to continue to work on the cost of it. And I think in the next, I don't know, maybe 2025, 2026, somewhere in that window, we'll start seeing some commercial 200 millimeter wafers in the market. And remember, 150 is very strong, so that brings a different challenge to 200. You can't go out with a 200 millimeter wafer that's more expensive per millimeter square or per area. So, and that cost roadmap is going down. So the 200 needs to catch where 150 is going to end up.
It's going to be quick on its tail. Yes,
exactly. So that puts a lot of pressure on the 200 millimeter development team. And but look, I mean, as we discussed, we've been at it for a long time. We feel really good about it. This team has never shied away from a challenge. This is a good one. And it's kind of fun because, you look at crystals when you're done.
Oh, yeah.
So that's the unique, I think, nature of this piece of the business. But, it's not easy to switch a fab from 150 to 200. We've done it in different diameters in our past, for sure. It's doable. But, when you have real commercial pull on the fab, and 150 is working really well, that's going to create a different dynamic. So it's not an overnight, hey, give me 200, my cost goes down.
No, it's not a flick of a switch.
No, absolutely not. And what I can say is we're really in good, connection with our communication with our customers. So each one has a different, plan to do so, and we keep them updated on where our volume and cost is, when it will be ready for full commercialization. And I think, as I said, in the next 4 or 5 years, we'll start seeing the transition happen in the market. But nobody's excited to buy an expensive 200 millimeter wafer.
No, of course, I know. Absolutely not. Absolutely not. And we talked about the milestones in the last 15 years, and how things are timelines are compressing. So I'm really quite excited about the next 10. Different wafer geometries. Different techniques, maybe, even different materials may be starting to be addressed. What as a generalization, what are you excited about for the next 10 years?
Certainly,
retirement, maybe. But
in terms of materials, Silicon Carbide has certainly a lot more to go, right? And we'll see a lot of innovative new techniques coming into the manufacturing of Silicon Carbide. I think each of them will add to the cost and the quality of the materials that we make. So I think, for me, the next 10 to 20 years is absolutely Silicon Carbide years. What could replace Silicon Carbide in above 600 volt high power applications? There are some reports of some materials, but I don't see anything that has the beginnings of a robust commercial platform yet. But
science projects.
Yes. I mean, I hate to call it because we were a science project at some point too.
32 years ago.
But yeah, time flies. But no, so, you know, in terms of high power applications, I really think Silicon Carbide is going to move into this space. And we've always said it, you know, above 600 volts all the way to, I think our demo was at 25 kV.
IGBTs,
yeah,
25 kV.
So, you know, all the way up there, Silicon Carbide has a fantastic runway. I don't see anything that's commercially viable that could intercept that in the next 10 years at least. But, you know, we're all in science and engineering, so never say never. But, you know, we kind of know most material systems, and Silicon Carbide has a fantastic longevity here. It's really, you know, it could block 10 times the voltage compared to silicon. You don't get that type of improvements, you know, year over year.
That's true.
They come every few decades, I think. So.
And you've got, you know, plenty. You said the early beginnings back at our start of our conversation. So, you know, on that, we really do, not only with Wolfspeed appreciate, and back in the Cree days as well, in the previous, but we really do appreciate what the materials business has done. And I think the whole industry can say that as well, because you have really, you know, the business has really enabled a complete industry. The materials is the foundation.
Yeah.
It's the stuff we don't see, it's below deck, it's below ground. We don't see it, but without it, we're going nowhere. So, you know, this has been a tremendous industry-changing development, and lots more to come.
Yeah, and you know, maybe one thing worth pointing out, from the very early days of us making the material, we've used it internally, we've also, you know, supplied externally. And I think that is an interesting dynamic. As a company, we've done that really well. Yeah. So there's a very good appreciation for our external customers and the feedback we get from them. And we also have a pretty fast feedback loop internally. So both, you know, circuits are really important, making the material commercially viable. So, you know, yes, we're growing internally, our device business, you know, gets our wafers, but we're also north of 70% in the power, I think, in terms of wafer supply to the market, which makes Silicon Carbide, you know, device business grow at a good clip. So it's exciting, as you said.
Tremendously exciting. And keep it edgy, keep it a bit mysterious, because it adds that sort of you know, edge to it. But you know, mention scale, mention quality, mention just sheer being there to drive this industry forward, because you know you're the guts of this industry, and it's been tremendous to talk to you.
Thank you, Guy. It's been a great conversation. Whether we like it or not, I think part of the dark art will remain with Silicon Carbide crystal growth. It was great talking to you. Thank you.
Pleasure. Cengiz, thank you for joining us here on In the Studio.